All right, today we're diving deep into the heart of industrial chemistry. We're going to see how engineers manage to tame, well, what you could call chemical fire, reactions so incredibly powerful they could melt the very steel that's supposed to contain them.
So let's just kick things off with a pretty wild question, one that chemical engineers have to solve all the time. How in the world do you control a chemical reaction that releases so much energy it could literally melt its own steel container?
Well, the answer is this incredible piece of engineering, a multi-tubular reactor. Now, you might look at this and think, hey, that's just a big heat exchanger. But trust me, it's a masterpiece of design, built specifically to handle insane amounts of heat, safely and efficiently.
Okay, Section 1, Taming Chemical Reactions. So first things first, we've got to understand the fundamental problem these amazing machines are designed to solve.
The whole thing boils down to this concept, the exothermic reaction. Basically, it's any chemical process that just unleashes a massive amount of energy as heat. And a lot of industrial processes, the ones that create the products we use every day, are violently exothermic. So the solution is just brilliant in its simplicity. You divide and conquer. You see, you can't contain one giant uncontrollable fire. So instead, engineers break that one massive dangerous reaction into thousands of tiny, manageable ones. Think about it like this. You can't control a raging bonfire, but you can control thousands of individual little candles.
And I am not exaggerating when I say thousands. Get this. A single one of these reactors can have up to 20,000 individual tubes. And each one is basically its own tiny, self-contained reactor. The scale is it's mind-boggling.
So how on earth do you confidently build something with 20,000 different parts? Well, that brings us to Section 2, Testing the Tiny Titan. And this is where the engineering gets really clever.
Instead of building the whole monster and just hoping it works, they start small. They build and test just one single tube, a perfect little replica of the thousands that'll go into the final reactor. By perfecting the performance of this one tiny titan, they can predict exactly how all 20,000 are going to behave. This quote from our source material really gets to the core of it all. Rate of heat generation and heat removal balance out when the temperature peaks. This is the critical balancing act they have to master. Let me show you what I mean.
Check this out. This shows that balance in action. When the reaction kicks off, the heat generation rate just skyrockets. But as things get hotter, the cooling system gets better and better at pulling that heat away. The temperature keeps climbing until it hits a hot spot. That's the peak, where the heat being created and the heat being removed are in perfect balance. The whole game is to keep that peak within a safe limit.
But of course, there's a villain in this story. It's called coking. This is basically soot, unwanted carbon deposits that slowly build up on the catalyst inside the tubes. It's kind of like plaque in an artery. It just chokes the reaction, kills the catalyst, and eventually you have to shut the whole thing down for a massive cleaning. So yeah, a huge part of the design is just trying to minimize coking.
Okay, so once that single tube test is perfected, it is time for the main event. Section 3, Building the Behemoth. This is where every single design choice has huge consequences for both cost and performance.
And right away, you hit a classic engineering trade-off. For those really intense, highly exothermic reactions, you need smaller tubes, about 25 millimeters. They give you more surface area to pull heat away, keeping everything under control. But for the milder reactions, you can get away with bigger, 80-millimeter tubes, and that drastically cuts down the cost of the reactor. It's this constant dance between safety and the budget.
Picking the right cooling fluid is also absolutely critical. It's kind of like leveling up. For temperatures up to about 300 degrees Celsius, you might use a synthetic oil like Thermanol 55. As things get hotter, you need tougher stuff like Thermanol 66 or Doutherm A. And for the really, really extreme reactions, above 350 degrees, well, engineers use molten salts. That's literally liquid salt flowing around the tubes, soaking up that incredible heat.
And inside the main shell, there are 3 unsung heroes that are essential. You've got baffles, which are basically plates that force the cooling fluid to flow evenly across all the tubes, preventing any dangerous hotspots. Then there's a catalyst support, usually just a simple spring or a mesh at the bottom of each tube to hold the catalyst in place. And finally, an impingement plate at the inlet acts like a shield, spreading out the incoming gas so it doesn't just blast a few tubes and cause problems.
So, the reactor is built, but how do you operate it? Section 4, the nervous system. Think of this as the brain and the nerves that keep that chemical fire perfectly tamed. Now I know this control diagram looks like a crazy spider web of pipes and valves, And, well, it is. But what's amazing is that the entire control philosophy, the whole strategy, boils down to just two simple, elegant rules.
Rule number 1 is dead simple. Control the pressure at the exit. There's a pressure sensor on the outlet pipe, and it's constantly talking to a control valve. That valve is always opening or closing just a tiny bit to maintain the exact pressure inside the reactor that you need for the reaction to work perfectly.
And rule number 2 is just as straightforward. Control the temperature with the cooling fluid. You've got temperature probes inside a few key tubes. If they sense the temperature creeping up, a valve opens and lets more cooling fluid flow in. If it's too cool, the valve closes a bit. It's this constant, delicate dance of feedback and control happening every second.
All right, we are almost there. The reactor is built, the controls are all hooked up. Now we get to the final and maybe the most meticulous step of all, loading the catalyst.
And this isn't just dumping a bucket of pellets in. Oh no. It's a super careful 6-step procedure. First, a sample of the catalyst is tested. Then, a support spring gets fitted into every single tube. They use a special method called sock loading to gently pour the catalyst in so it doesn't break. After that, a precise weight amount goes into each tube. Then, they measure the empty space at the top to make sure it's uniform. And finally, they check the gas pressure drop across every single tube. They all have to be within plus or minus 10% of each other for the reactor to work right.
So, the big takeaway is this. The multitubular reactor calms this immense chemical fire by breaking it down. It's all about controlling heat, one tiny tube at a time, and then multiplying that precision by thousands. It is such an elegant solution that combines meticulous detail with just massive scale.
You know, this reactor is just one piece of the incredible, invisible engineering that powers our lives. It really makes you wonder, doesn't it? What other industrial giants are out there, quietly making our modern world possible?